Hi, this video is one in which the main goal will be to explain what is meant by association between two quantitative variables which are paired, and how that results or evolves into our understanding of what we call correlation. Association in the context of chapter 4 refers to the way in which we describe how two variables that are quantitative and paired relate to each other. There are three aspects to this association between two variables. One is called form, the form of the relationship. That's a physical shape of the data, but we already used the word shape to describe one variable in histograms. We talked about shape being symmetric or skewed in chapter 3. So now we use the word form to describe the shape of data generated by two variables. And that shape is going to be determined by drawing something called a graph called a scatter plot. Another thing that the scatter plot will enable us to see is the direction of the form, especially in what we will call linear forms that we will describe shortly. And direction in linear forms can be one of two. You can have a positive direction, which implies a direct relationship between the values of one variable and another. And by direct, we mean that whenever we see one variable above its average value, we should see the other variable also above its average value and vice versa. Or we could also be talking about two variables that in a linear form have a negative association, and negative association is descriptive of inverse relationships between two variables. So when one variable is seen to be above its mean or average, the other one would be below its mean or average, and vice versa. In other words, they move in opposite ways. So those are the two particular directions of types of associative direction that we will be examining in linear forms. And then the third element of association in data relates to the strength of the association. And strength of an association is what really the correlation coefficient is mostly about. It's about measuring how well the linear form is, how well a line depicts the actual trend and patterns seen in the data, how linear the data is or conforms to a linear pattern. To the extent that a linear pattern allows you to describe how two variables associate, then the slope and the y-intercept of the line that fits the data should actually provide you with predictions or estimates that are really, really, really close to the true values of y observed, of the vertical axis variable observed. To the extent that that's the case, then the predicted values and the actual values of y would be so close that they would have a very low amount of total deviation between the two. So one of the statistics that we will use in order to compute how strongly X is able to describe or help us predict what Y will be something called the standard error statistic. That gets introduced in this chapter. Besides correlation, another statistic that tells us how well X does at explaining Y, we will learn about a statistic called the R-square statistic, more clearly known as the coefficient of determination between two variables, and that will be our other performance statistic that we measure in the course. So correlation will essentially be a statistic that applies for linear forms only. It's ideal in the case of linear forms. So when data are not linear, the correlation statistic is not going to be a very telling statistic about how two variables relate to each other. It will give us a false sense of association or weak or lack thereof. So it's ideal in linear forms. It is a measure of how well two variables move together relative to how much each varies on its own. And so a correlation statistic will have a sign. It'll have a positive value when there's a direct association. And it'll have an inverse form when the sign of the correlation coefficient is negatively or inversely related. In addition to that, it'll have a magnitude between -1 and +1 in value, inclusive. So a correlation coefficient will always be a number between -1 and +1. And that's because it is a statistic that comes from measuring how an individual data point varies from the average value, be it horizontal through X or vertical through Y. It is a statistic that relies on the measurements of deviations from the mean, and z-scores will play, standard scores learned about in chapter 3 will play a role at creating and identifying the formula that is behind the computation of the correlation coefficient. In your practical work in lab 4 and in quiz 4, correlations will be computed from data using StatCrunch, not by hand. It's very time consuming to be, and very subject to a lot of risks of making calculation or numerical mistakes to be doing correlation calculations by hand. So we will probably not be doing that in, or you shouldn't be doing that in your lab 4, quiz 4, or interpretive work or analytical work in exam 2A or exam 2B. However, the purpose of these videos is to actually walk you through the necessary steps to actually compute a correlation and then compute the elements and ingredients of a regression line. So let me outline those in the following slide. So a correlation statistic is actually more formally referred to as a correlation coefficient. And correlation coefficients are essentially ratios. That's what the word coefficient means, that there's a benchmark under that you use to establish what is the measurement of something in relation to this benchmark. So at the numerator of the correlation coefficient is how two variables co-move or co-vary. And the covariation is with respect to their mean, their respective averages. And in the denominator, we're going to be measuring how each variable varies on its own. So that's what a correlation coefficient is defined as. It is a measurement of the linear strength and direction of association between two variables by gauging how the two variables vary together relative to how they vary on their own. That is the shortest definition of correlation coefficient that I know of. You could always replay this back as many times as you want, or slow down the process of playing this slide. So here goes how we get to compute that in the next portion of this formula. So what we're going to do is we're going to set this line and we're going to measure how it is that we measure how variables covary. So we will have individual values of x, the horizontal factor, the so-called explanatory factor, and we will be comparing that to the mean of x for each and every value. And in order to establish how x and y covary, we will then take on a corresponding value of y that is paired or tied with the value of x in question. And for all of these pairs of x's and y, we are going to take the sum of these products of the deviations in x and y. And what we're going to do with that is we're going to divide that sum by how x and how y vary on their own. So it'll be the product of the deviations of x and the deviations of y. And as we may recall from chapter 3, a deviation or standard deviation is the average difference from the average value of a variable. And that is arithmetically computed by taking the square root of the variations in each variable. And those variations are calculated by taking the sums of how each value differs from the mean of each variable squared. So it is the squared deviations that help us compute that. And now I also have to generate how each value of the variable y, of the second variable, differs from the mean value of y. That is also to the power of 2. Let me make one correction here. Here we're interested in measuring how x differs, each and every value of x differs from its average, and how y differs from each and every value of its average. And in this case, we want to multiply the variations of one and the variations of the other. So we're taking the square root of the variations in x, as well as the square roots of the variations in y. And that's what we mean by correlation coefficient. R, the correlation coefficient, is calculated by taking how the two variables vary together. So I'm going to color code that in yellow. Divided by how each variable varies on its own. Both x and y vary separately here, and it is after you calculate how x and y vary from their respective means that you then multiply together the two variations into one single computation. Now, if you notice, both the numerators and the denominators have interesting characteristics or structures. The square roots at the bottom are what we call the standard deviations of x and y, respectively. So that if we bring these into the numerator structures, we actually get something very similar to the z-scores of x and the z-scores of y, which provide us with an opportunity to explore the relationship between how we measure association, R, and how R is really the average of 1 over n minus 1, the average of the sum of the product of the z-scores of x and the z-scores of y, of where the z-scores of the two numbers are co-located with one another. So another definition of the correlation coefficient is that the correlation coefficient is also the statistical average of the product of the locations of x and y in standard deviation units, in standard score units, z-scores. So there are two different arithmetic approaches at calculating the correlation, which will yield the same answer. In our own computational life, we're not going to be doing the arithmetic of all these steps. In our own computational lives, we're going to be going to StatCrunch. And in StatCrunch, we're going to be typing the following command. We're going to go to stat, Then we're going to click onto summary stats like we did in chapter 3. But instead of going to columns, which was the command we learned to use in chapter 3, we're going to use the command correlation. Upon entering this third item in the stat menu, stat summary stats correlation, you then are given the opportunity to tell the software where the variable called X is and where the variable called Y is located in your data table. So you have to have 2 paired variables in your data table in order to compute a correlation. So then you select the 2 variables that are quantitative, and then you compute. That's all there is to it. And it'll do the math for you. The software will then take care of the math of all the steps. And that's all there is to it. I hope that as you enter chapter 4 and look at the information of how you compute the correlation coefficient, that you also be aware that you should check for a few problems, as in what can go wrong in computing the correlation coefficient. So be sure that data is roughly linear in shape, roughly linear in form. Whether its direction is positive or negative is only going to impact whether the correlation coefficient sign will be positive or negative. That's not an issue, but the form of the data should be linear. If the form of the data is not linear, your correlation will actually have a tendency to be closer to 0 in value than have a meaningful correlation factor. So be sure that the data is roughly linear in form. Be sure you have 2 or more quantitative variables. You can't compute correlations with categorical variables. In categorical variables, we use the notion of dependence and independence, and we use conditional percentages in order to identify dependence. And the other thing you should be sure you have is be sure you have blatant outliers in the data. And if those outliers exist, you either have to rationalize their inclusion in the data or you have to exclude them from the data. But those kinds of precautions are really important in your work. So be very, very careful with them. And that's pretty much concludes the presentation of correlation. We'll do a couple of more videos on chapter 4, including how to run a regression and how to use correlation to actually meaningfully associate 2 variables to one another. So we will be going into greater detail in the coming videos for how you predict what will happen to one variable's locations based on the correlation and based on the other variable's location. How the z-scores of x help you predict the z-scores of y, and therefore how you can use the values of x, standardize, in order to make predictions about y. And this process that I just described here is the process called simple linear regression. The subject of our next video, where we use stat, regression, simple linear, where we select X and Y and other options in order to compute and get the resulting relationship statistics between X and Y. Thank you for watching, and I will see you in the next video.